This is a mini study session um, that's intended to go along with the ARRL's Amateur Extra Manual. We're currently using Rev 12, and this will be material from Chapter 4. Um, when we get to this point, I like to think we're finally getting into the meat of things. It helps explain ways and how things are done technically with ham radio. So it's uh, kind of different for most people because there's some abstract concepts that you have to understand, and hopefully this will help make it a little easier to do that. So if you remember back from the technician and general study sessions, we talked about Ohm's law, which is a relationship using just simple math that explains the way voltage, current, and resistance interact with each other. And this is just a little politically incorrect uh, image that my dad actually taught me when I was in grade school to remember Ohm's law, where, for example, it was if you're looking for the voltage or the electromotive force, the eagle, then it's the Indian times the rabbit, right here, V equals IR. If you're wanting to find the current, then it's the eagle over the rabbit, or V over R. And if you're wanting to determine the resistance, then it's the voltage divided by the current here, or the eagle over the Indian. So that's just a real basic way of using math so that we can analyze circuits and determine in a particular circuit. And in this case, at this point, they were all DC circuits. And to understand the relationship between voltage, current, and resistance, so we could figure out what goes on in the circuit. Now we're getting into inductors and capacitors, and even though you saw them in the general course, we're going to take a little more rigorous look at them here. And these are just some examples of inductors that you may find. Basically, in the most basic form, it's a coil of wire, and this is a schematic symbol. This is a variable inductor, and this is the schematic symbol for that. And typically on a schematic symbol, if you have an arrow, it means whatever value that is, that device, it can change its value. And this one here is a magnetic or iron core inductor, where the coil is actually wrapped around an iron core to get you different physical properties. And its schematic symbol is the coil with the symbol for an iron core. So that's the way they may look as you run across them in a circuit. And then there are capacitors, a lot of different types of capacitors, various sizes, various functions. They generally have two leads in some fashion, or two terminals that can be attached with wires. And the symbol for the capacitors, for example, here's an electrolytic capacitor. It's showing a plus sign because it is polarized. These two symbols, one's showing a fixed capacitor and a polarized capacitor. And if you're using a polarized capacitor, then you have to pay attention when you wire it that the proper lead goes to the proper type of the circuit. And then down here are variable capacitors used for tuning. We'll get into that a little bit later. So now we're going to take a look at reactance, and the symbol that's normally used for reactance is an X, whereas resistance is usually an R. And just like resistance, reactance is also a resistance to current flow, and it's measured in ohms. So if we look at a an inductor circuit here, what we have is a variable alternating current source, whereas when we were looking at resistors earlier, they were DC sources or direct current. Now we're looking at alternating currents, and we have a current flowing through the inductor. And what happens is as the current flows in one direction, it builds a magnetic field around the coil. And then as the voltage changes polarity, the current starts flowing in the other direction, and the field collapses and then is built again from the current flowing in this direction and alternating between north and south poles. So if we look at what inductive reactance is, this resistance to current flow as a function of frequency, if we start out at DC, the inductor looks like a short circuit. So there is no resistance to current flow. It'll flow just as if it were a straight piece of wire. And then as we increase frequency, the inductive reactance increases linearly here. As we go up higher and higher in frequency, the inductive reactance increases, and it increases per this formula where the inductive reactance is 2 times pi times the frequency times the inductance of the coil. And so whatever, if you have a fixed inductor, all you have to do is know what frequency you're operating at, and you can calculate the reactance by 2 times pi times the frequency that you're at times the inductance of the coil. And the thing to really understand is that the reactance of an inductor depends on frequency. As the frequency changes, the reactance changes. And the way it changes in an inductor is that the linear function, just a straight line like this. The other thing to remember about inductive reactance is that it is positive. If you have an inductor and you calculate the reactance, this reactance will be a positive number. Okay, now we're going to look at reactance for a capacitor. Here again, as a reminder, reactance is indicated by the symbol X, and it is a resistance to current flow measured in ohms. So let's take a look at a capacitor. And the way it's built is that it's essentially two parallel plates of conductor with a dielectric in between them that's connected to an alternating current source of some sort. And what happens here is that the reactance of this capacitor can be calculated, X sub C, as 1 divided by 2 times pi times the frequency times the capacitance in farads. And if you'll notice in this formula, the frequency is in the denominator. So as if you're at zero frequency or DC, then you're way here at 0, and the reactance in ohms is near infinity. And then as you increase the frequency, the reactance for the capacitor decreases and comes down this curve. And if you get to a high enough frequency, the capacitor appears to be almost a short circuit. So it does DC, it appears to be an open circuit. Current can't flow through it. And then as the frequency increases, the reactance decreases and you get more and more current flow until it almost appears to be a short circuit. So just as a reminder, the reactance here for the capacitor also depends on frequency. And capacitive reactance is negative. Now, if you recall, previous slide, the inductive reactance is positive, and that's going to be a key thing to remember as we get into this a little bit. Actually, on the next slide. I've got a little problem here. This is what happens when you use cheap help. It's not advancing. Okay, so now we're going to take a look at impedance. It's just like resistance, only different. And that's we're going to take a look at this circuit here. What we have is a series RLC circuit. R standing for resistor, L for inductor, C for capacitor. And this is how it's wired. We've got a resistor in series with an inductor, in series with a capacitor, and they're all connected in series back to the alternating current voltage source. Now, what happens here is we've still got the same graph with frequency, and now we've got a graph of both the capacitive reactance and the inductive reactance as the um, uh, on the same graph. And we go back and take a look at the capacitive curve. When we're low, very low frequency or zero, we have very high reactance. And then the capacitive reactance decreases as we increase frequency. And then if we look at the inductor in the circuit, then we're at a low frequency. The inductor is essentially a short circuit. And then as we increase the frequency, the reactance of that inductor increases. Now, if you recall, I mentioned that the capacitive reactance is negative and the inductive reactance is positive. Now, why that's important is because in a series circuit like this, these values, the resistance and the inductive capacitance and the inductive reactance and capacitive reactance add. You just add this plus this plus this. So what happens is we're here adding the inductive reactance to the capacitive reactance. So when we're at very low frequency, we're primarily having capacitive reactance. We have very high capacitive reactance, and then as the capacitive reactance decreases, the inductive reactance increases. And since the inductive reactance is positive, the capacitive reactance is negative, and we're adding them, then the total reactance gets to a very low number. And at this point, where the inductive reactance and the capacitive reactance are equal, they cancel each other out. So that the only thing you have in that circuit when these cancel each other out is just a resistor. And this is called the series resonance point. And this concept of resonance is probably one of the most important things to understand as you get into a lot of the technical part of the ham radio. This is especially true in antennas where the resonance point is critical in understanding how your antenna operates. It's also important in tuners and tuning, frequency tuning. It just pops up all over the place. So this idea that there is a resonance point where the inductive and capacitive reactance cancel each other out is really important to understand. Okay, so just taking a look at resistance to the current flow. Resistance does not depend on frequency. Reactance depends on frequency, and the inductive reactance is positive, and the capacitive reactance is negative. And so your impedance, what impedance is, it's the sum of the resistance and the reactance. Okay, so just think about that a minute. The impedance is the resistance plus the reactance. Now at DC, the impedance and the resistance are the same because there is no reactance. And then also at resonance, the impedance and the resistance are the same because there's no reactance there because they both cancel out. So then we get into the math here a little bit. And, an obvious question would be, why do we need to describe impedance mathematically? And if you remember back through in the technician and general sessions, we took a look at series circuits and parallel circuits. And we were able to calculate the voltages in a series circuit in this situation, the current flows using Kirchhoff's current laws in a parallel resistor circuit, and all this was DC. Ohm's law that we studied early on, V equals IR, I equals V over R equals V over I, and the power calculations of either the power being the current times the voltage. All of these are DC values. And what we need to be able to do is to use these same concepts with circuits that aren't DC. Instead of a 9-volt battery that delivers a direct current, we need to have a way to do calculations in circuits that has an alternating current source. So that's basically the reason for the math that we're about ready to go through, so that we can use these same concepts to understand circuits that vary with frequency. So it's doing the same thing we did before. It's just going to be a little bit more complex because of the alternating current. And it's not really all that complex, which is what I hope I can show you next. Okay, now we're going to take a look at a little bit of the math on impedance. And the formula for the impedance, like we mentioned earlier, is that the impedance is just the resistance plus the reactance. But we're going to plot these on a graph a little differently than just adding the two together. And what we'll do is we'll start here with a rectangular coordinate system. And the horizontal line here is the x-axis, where x is 0. And the vertical line, usually you would be, you're probably used to seeing it as the y-axis, but here we're going to call it the j-axis. And really not going to get into why that is. It's just no difference than a y. It's just a convention we're going to be using. So we've got the origin here, where x is 0 and j is 0. And then this is positive x. Going to the left is negative x. And then going up on this axis is positive j, and going down is negative j. So we're going to graph this impedance by starting on the x-axis, where the resistance is plotted. And in this case, we have 1, 2, 3, 4, 5 ohm resistor. And we're going to represent that 5 ohm resistor as 5 units here. And then we're going to plot the reactance, which in this case, this is an inductive reactance because it's positive, and this reactance is 1, 2, 3, 4, 5, 6 ohms. So the impedance is this line here from this point here at the, hold on. So the impedance is this line, Z, which is the hypotenuse of this triangle. And this is the inductive reactance, and this is the resistance. So we're graphically showing the impedance on this rectangular coordinate system. So the impedance is R plus JX is the way that that's described. Another way of describing the impedance is describing it as Z, which is the magnitude at this angle A. So you can either describe the impedance as this in rectangular coordinates, resistance plus J reactance, or you can describe it as the magnitude of the impedance here, the blue line, add an angle A. That would be that angle right in here. And I'm held up again. Okay, so now we're going to take a look at how we describe an impedance using these two different graphical and mathematic approaches. So the first thing we're going to look at is answer the question, why do we need two ways to describe an impedance? And it's really pretty simple. We need the impedance described in these two different ways so that we can do the arithmetic necessary to solve the circuit problems. So let's say, for example, if you want to add two impedances, and that would be a series circuit. The impedance number one would be R1 plus JX1. So that's a resistor plus a reactive, a reactance could be the capacitive or inductive. If it was capacitive, this would be a minus rather than a plus. So what we want to do is we've got impedance 1, and then we have another impedance 2 that's a different resistance and a different reactance. And we want to add those two together. So what we do is just add it. The impedance total would be this right here, R1 plus JX1, R1 plus JX1, plus R2 plus JX2. And then regrouping, the impedance total would be R1 plus R2, and then it would be JX1 plus X2. So that's the reason for using the rectangular coordinate system. If you have an impedance that's in this rectangular coordinate system, it's very easy to add impedances this way. Now, the other polar coordinate system is used if, say, we want to multiply two complex numbers in AC power. A complex number is, an impedance is a complex number, voltage can be a complex number, current can be a complex number, meaning that it has a magnitude and an angle. It can be described as a magnitude here at a particular angle. So that's what's meant by a complex number. These are complex numbers, and this is a complex number because it's described as the magnitude, this blue line here, at a particular angle. So let's say we have a voltage that is this magnitude at this angle, and we have a current that is at this magnitude and this angle, and we want to compute the AC power from these two values. All we have to do is multiply the voltage times the current, V1 times I1, and then to get the angle between the two, we just add the angles. So we take A1 and add it to A2, and then that'll give us the power as a magnitude and an angle. You could do the same thing. Let's say you had complex numbers here. Say you represented the voltage in rectangular format as R plus JX, although you would be doing the voltage, and you can take this times this, but it's pretty involved to do that calculation because you got to multiply this times that plus this times that, and then this times that plus this times that. Whereas if you convert this to polar coordinates, then it's just a matter of multiplying the magnitudes and adding the angles. And that's the only reason why we would use the two different types of coordinate systems, just so we can do the arithmetic to solve a circuit problem. So you're either able to represent your values in a rectangular coordinate fashion like these, or polar coordinate fashion like these. And when you're doing the polar coordinates, remember you're doing the magnitude of the value at some angle. And when you do the rectangular coordinates, you're just doing the x and the y, the r and the x in this case. And that's all there is to complex numbers. It's that simple. And I think that's about all I know. So we'll see how this goes.